Right, welcome everyone to the December talk for the Manchester and District branch of the Institute of Physics. You're all very welcome. Those who regularly attend these will know that because of COVID, we've had to move our talks remotely. We normally do those at the Brooks building of Manchester Metropolitan University. And in fact, tonight's talk has been rescheduled from February. Tim was one of the first casualties of the COVID pandemic. He found himself having come back from abroad. I think it was in Singapore, Tim.
Yep.
He had to self-quarantine, and the rest is history. So we're extremely grateful that he's agreed to do the talk remotely, do that tonight. And we have found this format very useful. It's enabled us to expand our audience and have people from a wide range of places, including from abroad. So everyone is welcome today. We've got something like 172 people registered for the talks. That's very good. We're hoping to do these talks like this in the foreseeable future, but perhaps we'll return to some face-to-face talks in the autumn of 2021. So I'm going to introduce you to Professor Tim Spiller. He is Professor of Quantum Information Technologies at University of York. He's been there since 2014, and he was a founding director of the York Centre for Quantum Technologies. He's now director of the UK Quantum Communications Hub. He was born in Birmingham, I've just found out, and I've told him that nobody's perfect. He did his first degree at Oxford, and that was in physics, and he started off as a particle physicist, and yet another person that's been seduced by the dark side and has ended up getting involved in quantum technologies. So prior to York, he was at Leeds, and he's also worked for Hewlett-Packard in Bristol, and has a long distinguished career in this field, 35 years in researching quantum theory. So Tim, you're very welcome. We will start the talk in a second. At the end, there will be a chance for people to ask questions. There is a chat box at the end if people want to, or there's a question box if people want to ask questions. Myself and my colleague Anna will be collecting those, and we'll try to have perhaps a few questions at the end, see if Tim's willing to answer those. So thank you very much, Tim. We're very grateful to hear this talk tonight. I'm very excited about it, and off you go.
Great. Well, thank you very much. Thank you, everyone, and it's really nice to have the opportunity to tell you a bit about quantum technologies. I hope by the end of the talk, I will have explained a little bit about what this quantum communications hub is in the UK, but I'll start general and focus on quantum communications in particular in a few slides time. So the idea of the whole talk is that I was working it out. It's 43 years since I actually went off to university to start learning about quantum physics and everything. And the quantum physics hasn't changed at all in that 43 years. But what we can do with it has changed a huge amount. So we now know that there are new technologies that we can build, and these are already appearing based on quantum physics. And these give us some kind of advantage or some new feature that ordinary information technology doesn't. And so I'll try and explain just a little bit about that in general, because there are all sorts of examples. There's computing, there's sensing, there's imaging, and there's communications. And so I'll try and give a very quick overview, firstly of the relevant bits of quantum physics that underpin all of these, but then what all of these things mean and where they get their quantum advantage. But then I'm going to focus in on quantum communications. So I'm going to tell you about that particular area, what we're doing in it in the UK, but I'll try and explain how it works first, and then tell you a little bit about what's happening in the UK national program. And so that's the idea. I've given myself quite a lot to get through, but I'll do my best. So the very first slide, I thought people presumably have some physics interest, and so as I said, it's fundamental features of quantum physics that underpin these new technologies. And basically, I have the whole of your first quantum physics course in one slide coming up. So this is the way the quantum world works, and these are fundamental features. So as I say, these were discovered early on in when quantum physics was first developed, but we now know we can use them in really interesting ways. And I'm going to use basically two out of the three I'll tell you about in this slide in the rest of the talk, so I'll say a little more. So the first one is the idea of superposition. And the idea of superposition is that quantum systems can simultaneously exist in more than one state. And we'll come back to that for the case of a single bit, a quantum bit. But the interesting thing for quantum computing, which is not the subject of this talk, but this is a very interesting thing, that the more quantum things you put together, the greater the number of different amplitudes or states you have in a superposition. And that grows exponentially with the number of quantum resources that you have. And that exponential growth is what underpins quantum computing. So we'll come back to the superposition principle in a few slides' time. The next thing, I've called it quantum uncertainty here, but the basic underpinning feature of quantum physics that this is about is the irreversible disturbance due to measurement. So if I take a quantum system and I try and find out something about it by measuring it, I irreversibly disturb the state in doing that. And that's built into nature. It's not the fact that experimentalists are still a bit clumsy and they'll get better. It's actually built into nature. And so we'll come back to this because this irreversible disturbance in measurement is very useful, and it's what underpins quantum communications. The third thing, which I'll mention but won't say a lot about in the rest of the talk, is entanglement. And this is an intimate relation between two or more quantum systems, even if they're very far apart, in that they are intimately linked, in that their state is only one between the two, if you like, and you cannot prise them apart into a state for one and a state for the other. I made this flippant cartoon actually quite a while ago now to suggest that these two people, Alice and Bob, could share an entangled state on other sides of the world. And in fact, I'll come back to it later in the talk. This is not so much of a daft cartoon as it was when I first put it together. So we'll come back to that a bit later in the talk. Okay, so quick tour of quantum technologies. And so the first thing is I mentioned superposition, and the idea that underpins quantum computing is that if you can prepare a system in very many amplitudes, so something that is a bit like a computer but actually works according to quantum laws, if you can prepare that in a superposition of many different amplitudes, you can compute something on all of those amplitudes at the same time. So you can do something in parallel with very many quantum amplitudes, and that very large number of parallel amplitudes, this exponentially large number of amplitudes, enables, in some sense, better computing. Certainly things that we can do with a quantum computer that we can't do with a conventional one. There are all sorts of applications. Simulation and modeling, cryptanalysis, solving some complex mathematical problems. I'll come back to that, searching through databases. So there are very many algorithms now that people have worked out that you can run on a quantum computer that ought to give you some sort of advantage. What are they made from? Well, trapped ions, possibly semiconductor devices, certainly superconducting devices, light, all sorts. And clearly, I think you will have heard in terms of quantum advantage that Google and IBM have just about got there with superconducting devices. There was a recent experiment announced in China where a specific device based on light has actually got to the point where they can solve a problem with their computer, if you want to call it that couldn't be solved on a conventional computer. So we're just about at the point now where this quantum advantage is just about beginning to show. So that's a quick comment about quantum computing. In terms of imaging and sensing, if you take non-classical states of stuff, which might be light or atoms or whatever, then certainly an entangled state would be one example. If you've got two things that are entangled and you bounce one of those off some object and then you do something clever afterwards, combining those two or comparing the data that you get from the two, then you can sense or image things actually better than you can do if you use those same resources in a conventional sense. And well, what do people use? People sometimes use light for this. They might use atoms if they're trying to probe gravity. They might use a tiny nanomechanical device that they put in a non-classical state if they want to wobble that around and probe external fields that are applied to it. So there's all sorts of interesting sensors and imaging devices that can be built. The final one, which is going to lead me into quantum communications a little more, is this idea of this irreversible disturbance that happens when you try and investigate a quantum state. And the idea is that, and the two people in quantum comms are always called Alice and Bob. So Alice is always trying to send stuff to Bob. Well, the bottom line is if Alice sends quantum things to Bob and somebody tries to measure them en route, then they will disturb them. And that means Alice and Bob can work out what's going on. And so I'll talk through this in more detail in the rest of the talk. And what do we use for quantum communications? Well, basically, we always use light of some form or another. Maybe single photons, single little quanta of light, maybe other states of light, but we use light for quantum communications. So what I'm now going to do is talk a little more about the two relevant principles of quantum physics, the underpinning features, superposition and measurement that assist us in quantum communications. Then I'll explain how quantum communications work, or I'll give you one example of that. And then I'll tell you a little bit about what we're doing in the UK national programme towards that. So let me now take a step back and talk about the individual components that we use. And in quantum communications, we essentially use these things one by one, bit by bit, if you like. So I want to start off by talking about the quantum analog of a single data bit. So in ordinary information technology, whether it's in computers or phones or communications, whatever, data essentially always gets encoded digitally now. So that means it gets encoded into a string of zeros and ones. That's how we process data, store it, communicate it. Everything is now essentially done digitally. And the reason something is called a bit in ordinary information technology is because it's a binary digit. It has two choices. It can be a 0 or it can be a 1. And so in ordinary information technology, everything works in terms of zeros and ones. And so what I now want to do is talk about the quantum analog of that. And the quantum analog of a single bit, a single conventional data bit, is actually even more interesting than the, if you like, standard data bit, in that a quantum bit has a lot more freedom to it. And if you think of the two ordinary states of a conventional bit and labeled as 0 and 1, then a quantum bit can actually live anywhere on the surface of a sphere, where a conventional bit only knows about the North Pole, let's call that 0, and the South Pole, let's call that 1. So an ordinary data bit only has two possible points accessible to it. That's the space in which it lives. A quantum bit has the whole of the surface of this sphere on which it can live. And so it has, an infinite set of possible states that it can occupy, compared to just the two that an ordinary bit can occupy. And because of that, as far as a quantum bit is concerned, we could take two states opposite each other on the equator, and we could call those 0 and 1 instead. So I've labeled those red 0 and red 1 to make the distinction between the conventional bit states that are the North Pole and South Pole. But in fact, any opposing pair anywhere on the surface of the sphere are equally good to represent 0 and 1 as far as a quantum bit is concerned. And so let's have a think about this state red 0, which is on the equator. As far as an ordinary bit's concerned, this state doesn't exist. It doesn't have any access to it. But a quantum bit can be in this state red 0, and this is a very interesting state because this is what illustrates superposition. This state on the equator actually is in a superposition of this bit state white 0 and this bit state white 1. And so, if you like, it's like a musical note that has many harmonics to it. Well, our musical note here just has two harmonics, has white 0 and white 1. So we can decompose this red 0 and this red 1, and in fact any other state sitting on the surface of this sphere, we can decompose it into an amplitude for this white 0 and an amplitude for this white 1. So if you like, this bit state red 0 is carrying some information about the white state 0 and the white state 1 in parallel at the same time. It's in a superposition of those two. And that superposition principle, and in fact, these four states that I've chosen to illustrate here are going to be very useful for us when we talk about quantum communications in a few minutes' time. And so that's the idea of superposition, the fact that a quantum bit has much more freedom. It can live anywhere on the surface of the sphere. So let's think of a few examples now, just to get things going. So here are a few examples of quantum bits that people use. I've already mentioned a few when I spoke about the various quantum technologies. And where I can, I've tried to also sketch the red ones as well as the white ones. And so one thing that people use certainly in quantum computing for quantum bits is they use atoms, which might be neutral atoms, or they might be charged. They might have an electron removed or whatever. They might be trapped ions instead. But basically, people take a couple of energy levels in an atom. So an atom has very many energy levels, but people take a couple of them and they'll use those to represent the white 0 and the white 1. So this one's supposed to be a bit bigger to show it's excited compared to this one. Now, I can't really draw a superposition of those two, so I haven't tried to do so, but people can manipulate these and put them in a superposition of these two. So in terms of matter, people use atoms and ions as quantum bits, certainly in some candidate quantum computing systems. If we think about light instead of matter, then first of all, let's think about trapped photons. So a photon is the little indivisible quantum of light at a particular frequency, and those photons can propagate, they can travel, but we can also trap them in little cavities. So if we take a cavity that is empty, apart from the vacuum fluctuations that are always there in the electromagnetic field, we could use that to represent white 0, and we could stick one photon in the cavity, and we could use that to represent white 1. Again, it's quite hard to draw the red ones, but it's a bit easier when we think about photons traveling, so quanta of light traveling, and this is relevant for quantum comms. We can use the linear polarization of a photon, whether it's horizontal or vertical, to represent 0 and 1. And here the red ones are easy to draw because they're just the plus and minus 45-degree polarizations of that photon. So here it's very easy. Or you could use the left-handed and right-handed circular polarizations. You've got plenty of choice around that equator. So you can use different states, but here we'll pick on the linear polarization example. So traveling photons, you can represent 0 and 1 quite easily. You can also represent which path. If you've got some kind of interferometric device where a photon propagates through something, whether it goes to the left or whether it goes to the right, can be used to represent 0 and 1. And I've tried to draw the red ones here because photons, if you put them through a beam splitter, can go through both paths at the same time. And whether they do that with a positive relative phase or with a negative relative phase, then that can illustrate the red 0 and the red 1. So traveling photons are very useful, and we can represent 0s and 1s in different ways with those. If we think back to matter, then if I think about something like an electron as well as a charge, it has a tiny magnetic moment due to its spin. And if we stick that in a magnetic field, then the two preferred energy eigenstates of an electron are either parallel or anti-parallel to the field. And so those could represent the 0 and the 1 of a quantum bit, but the red ones are easy to draw here. We just point the electron orthogonal to the field, and whether it points that way or that way, orthogonal to the field can represent the red 0 and the red 1. So that's one way to use electrons, if you like, to represent quantum bits. Another way is to stick them in a tiny bit of semiconductor, so something called a quantum dot. And if you have a little bit of semiconductor with a barrier in, then whether you put an electron one side of that barrier or the other can represent 0 and 1. And because there can be tunneling through the barrier, then I haven't tried to draw the superposition, but tunneling through the barrier enables the electron to be both sides of the barrier at the same time, and you can pick a couple of those states and use those to represent the red 0 and the red 1. And if this was a superconducting device, then as a now used in quantum computing candidates, then this would in fact be 2e rather than e, because in superconductors electrons travel around in pairs, so-called Cooper pairs. And so you can build these devices, semiconductor or superconductor. And the one thing I want to emphasize now is that all of these systems work. So these examples that I've given you are not just theorists' sort of dream. They are now reality, and there are hundreds of laboratories all over the world where people are now, certainly at the single quantum bit level, can manipulate all of these different systems. And so they, at the 1 quantum bit level, they have exquisite control. They can pretty much take 1 quantum bit, whether it's a trapped ion or a photon, and they can stick it wherever they like on the surface of that sphere on which the quantum bit lives. They have that level of control now over single quantum bits. And clearly they're progressing towards multiple quantum bits by building a model quantum computers now, but certainly at the single quantum bit level, the laboratories all over the world that have this exquisite control over individual quantum systems. And that's certainly something that has developed since I was a student learning about quantum physics for the first time. So there are a few examples. I now want to come to measurement, and then I'll talk a bit more about quantum communication. So I've spoken about superposition and the sphere. I now want to talk about what happens when we actually try and measure a quantum bit and ask it a question, because we will disturb it, and we're stuck with that. That is built into nature. It's not something that's going to go away that we can improve upon. This fundamental disturbance is actually built into quantum mechanics, and in a sense, it's just as well that it is. Otherwise, there would be an inconsistency, I think, between quantum mechanics and relativity. So that kind of gets rescued by the irreversible disturbance that gets built into measurements. And so it's something that I think nature has taken care of and built in for very good reason. Now, measurements, if there's an unknown quantum bit sitting in a box somewhere, the only way you can interrogate it is to measure it. Unless someone tells you what state it's in, if you need to find that out for yourself, the only thing you can do is measure it. And so that's the only way to get information out of a quantum system. And so that disturbance, if you like, is a form of decoherence. It's going to mess up the quantum system. Now, the one thing that you can do as the person who does the measurement is that you can choose which question you want to ask. So if you've got a quantum bit in a box, you can choose to ask it the question, are you a white 0 or a white 1? Or you can choose to ask it the question, are you a red 0 or a red 1? You can't actually ask both of those questions at the same time because those measurements are not compatible. The measurements don't commute with each other, but nevertheless, you can choose which of those you wish to ask. So that's the thing that's open to you. You can make that choice. However, out of the possible set of outcomes that could come from that measurement, what you get is random. This is where the quantum disturbance comes in, and that's where the randomness is built into nature. It's genuinely random. And so let's take an example. So here's my sort of clunky cartoon of doing a quantum measurement. Suppose we take a quantum bit in this state, red 0 on the equator here, and we're going to ask it the white question. We're going to ask it what its bit value is. Are you a white 0 or a white 1? So here we set up, we've got our quantum bit, we send it in. And what happens is that simultaneous with the measurement projecting to tell us we've got the value 1, the quantum bit gets projected to the white 1. So it gets moved from here down there. So that's what happens. The state changes, and it changes in an irreversible way because you set up and run that experiment again. Exactly the same apparatus, exactly the same input state, send it in, and this time you might get 0 instead. And then what will happen is that you'll project this red 0 up there to a white 0. And which of those two you get in any one event is genuinely random. It really is. And so here already it actually is a flippant example of a quantum technology, because if you take a proper version of this and box it up, this is a quantum random number generator. If you take quantum bits repeatedly prepared in a state and you measure them suitably, so you prepare in a superposition of the two possible outcomes, then you will get a random answer. And if you do that many times, you'll get a random string of numbers. So that is a simple quantum technology that you can actually buy now if you wish, and that is a quantum random number generator. So that randomness is built into nature, and it's very useful in application in quantum communications, which is where I'm going to go now. So the basic idea is that this unavoidable disturbance is going to expose anyone who looks at your quantum bits when you don't want them to. At least you'll find out that they're having a cheeky look when they shouldn't be. And so the idea is that Alice sends quantum bits to Bob. if the eavesdropper, who obviously is called Eve, has a look in the middle, then she's going to find that she can't avoid disturbing those quantum bits. So I'll come to that in a minute. But first of all, what I want to do is illustrate how if we can use quantum physics to share information between Alice and Bob, then they can use that for secure communication. So let's go back to cryptography. So this is not quantum. This is just a simple bit of mathematics just to illustrate how Alice and Bob can communicate securely if they already had shared secret information. So if Alice and Bob have the same shared sequence of random bits, and this is called a key, if Alice and Bob share the same key, then they can use that key to send a message securely from one to the other. And here's how it works. It's really rather elegant, but simple. So if Alice takes her message, which of course is written in binary because we do everything digitally these days, if Alice has a message that she wishes to send secretly to Bob, she takes her key and she writes it out. So she needs as many random digits of key material as there are digits in her message. And she just writes the key out underneath it. And then she just does bitwise addition. So 1 plus 1 is 0, and you don't do any carrying. And 0 plus 0 is also 0. And 1 plus 0 and 0 plus 1 are 1. And so Alice just does bitwise addition, no carries. And she gets what's called a cryptogram. Now that she can send to Bob. And so she sends that to Bob, he receives it. He's got the same key, so he writes it out underneath in exactly the same way, does bitwise addition with no carries, and out pops a message. Because if you add 1 twice or 0 twice, you get back to where you started in binary with no carries. So it's really elegant bit of mathematics that is in fact information theoretically secure as far as the transmission is concerned, because if the key material that Alice and Bob have is just a random string of numbers, then the cryptogram, as it's called, is also just a random string of numbers. So if Eve sees the cryptogram, all she can do is guess what's in it, because she just sees a string of random bits. So the only way Eve can learn anything is to try and learn about the key that Alice and Bob have previously exchanged. And so being able to communicate securely really kind of boils down to being able to share keys securely. And you can use keys for all sorts of things once you've exchanged them. But let's think about secret messaging for just a minute. So the idea is that Eve needs to know the key. Now, the problem is if Alice has previously sent Bob the key by conventional means, how does she know that Eve hasn't intercepted it? You know, whether it was on a memory stick or written down or whatever, Eve might have had a cheeky look when that key was communicated from Alice to Bob. So what you really want is a way to share key material between Alice and Bob, where you can then have an assurance that Eve hasn't been able to have a cheeky look and learn any information about your key. And that's where quantum physics can be employed to help out. So the idea is called quantum key distribution, and the idea is that Alice and Bob use quantum bits to establish a shared key, and Eve is going to get caught if she tries to have a cheeky look. And so let's try and work out how that could go through. The example I'm going to choose is actually called BB84 after Gilles Brassard and Charlie Bennett, who invented this protocol in 1984. There are other ones that one can use, but this one is nice and elegant, and it is actually used in many of the technologies that are actually operational now. So it's a good example to give. The basic idea is that Alice has to send stuff with some redundancy built in. And so in BB84, Alice actually chooses at random to send Bob one of these 4 states. That's white 0, white 1, red 0, or red 1. So Alice chooses randomly to send Bob one of these 4 states, and she can use a quantum random number generator if you like to choose which one she sends. And she does this very many times. So I'll just do a short example, but Alice does this very many times. So here's what happens. Alice sends a load of these numbers across to Bob, and That's fine. Now suppose that we have an eavesdropper in the middle. Well, the eavesdropper doesn't know what's coming. And so the eavesdropper doesn't know whether to ask, as a quantum bit is flying past, whether to ask it the white question or the red question. Are you a white 0 or white 1 or a red 0 or white 1? She has to guess. She has no prior information on what's coming. So she has to guess as to which question to ask. So here's what happens now. If Eve is going to intercept these quantum bits and measure them, then what she finds is that some of the time, and she won't be able to escape, some of the time she'll guess wrong. And so she will have asked the wrong question, if you like. So in this second one here, she interrogated a red 0. She asked it the white question and she's projected it to a white 1. And this one, the same and the same. So she's introduced 4 errors here. And she can't avoid that. That's built into quantum physics. And so at this point, you're probably thinking, but Bob is stuck because Bob can only do the same thing as well. And that's true. Bob is not in the knowledge of what's coming. So Bob has to choose randomly which question to ask as well. And that's very important. So Alice has built in redundancy. She's sending white stuff and red stuff. And Bob doesn't know which question to ask either. However, Alice and Bob can then publicly communicate afterwards. So by public communication, I mean effectively over some kind of authenticated channel. So Alice and Bob have to be sure that they're talking to each other, and I'll mention authentication again a bit later. But they can assure by some means that they are talking to the right person, and someone is not impersonating one to each other. It's called a person in the middle attack. As long as Alice and Bob have authenticated with each other, then they can do some clever stuff. First of all, they can work out which data to keep. So what Bob does after he's done a load of measurements on many quantum bits that Alice has sent to him is he announces which questions he asked. He doesn't announce his answers, but he announces which questions he asked. So he says, I did the red question on the first quantum bit, white question on the second one. So now Alice knows what she sent, and so Alice can tell Bob which data to keep, and she obviously chucks away the ones that Bob is going to chuck away as well. So without revealing any of their data, they can work out which ones to keep, which is clever for a start. Then they can sacrifice a bit of the data they've chosen to keep publicly and determine if the eavesdropper's been at work or not. And so they just compare some random selection of a few quantum bits, and they can work out the error rate. And if they see errors, some of them will clearly be just due to the fact that the transmission didn't quite work properly or Bob's measurement wasn't perfect. But nevertheless, if they see errors, they will assume that all of these are due to eavesdropping. So they take a worst case scenario and assume that Eve has been at work. Then they can do further clever stuff, actually. Without revealing all of their data, they have to sacrifice a bit of it, but without really revealing all of it, they can send subsets of the data, so products of various bit values and parities and things. And they can work out where errors are in the transmissions that they've both chosen to keep, and they can correct those errors or remove those bits. And so they can actually find and correct errors. And then at the end, having error corrected what they've chosen to keep, they can then distill their kept data down to a shorter length of data, which is guaranteed to be secure with some security level. And so they can do all of that by conventional communication after they've done the quantum part of the communication. And then they end up with a shared key where they have a guarantee about how much of that key the eavesdropper can possibly know. So then they can use that as a one-time pad, like that little example I've just given for secure communications, or they can use it for other things, which I'll mention in a few slides' time. So here's a specific example. I mean, this is a kind of working example how Alice and Bob would implement this with light. So Alice could choose to send photons to Bob or light signals that approximate single photons to Bob. And she chooses them at random from the 4 possible polarizations, vertical, horizontal, and plus minus 45 degrees. And Bob asks the white question, which is vertical, horizontal, or he asks the red question, plus minus 45 degrees. So he measures in these 2 polarization bases. And then Bob tells Alice which basis he chose to measure in polarization-wise, bit by bit, and Alice tells him which ones to keep and which ones to throw away, and then they can agree a protocol. So here's the kind of example of a start of a transmission. Alice sends these polarized photons chosen at random in one of these 4 states to Bob. Bob chooses to do these measurements at random. He doesn't know what's coming, so he just guesses. And then when he happens to have measured in the basis that Alice chose to send in, and he tells Alice that, she'll say, well, keep that one because you should have got a faithful answer there. And so they'll keep that and they'll assign that a bit value 1. They'll reject that one because those Bob measured in the wrong basis compared to what Alice sent, and so on. And so you can see how they begin to build up their raw quantum transmission, as it's called. And this is their kind of embryonic key. And then they have to do comparison, sacrifice a bit of it, then they have to work out where the errors are, remove those, then they have to compress it down to get the final key. But this, if you like, is the start of the transmission. And I should point out that you might think, well, can't Eve do something rather more clever than just intercept and measure? Can't she clone a quantum bit as it goes flying past? Well, she can try to do that, but she will introduce errors by cloning as well, because you cannot clone quantum things without introducing errors. You can't do that perfectly. So kind of doesn't matter what Eve does. However she tries to get around this irreversible disturbance due to measurement, she's going to get caught. So if we assume that she chooses to just measure, then she measures either in this basis or this basis, the same as Bob. Now, if you think about it, out of the results that Alice and Bob keep, Eve is going to guess wrong half of the time. So she will have corrupted half of the stuff that ends up at Bob. However, that corrupted stuff, because Bob is measuring in the correct basis that Alice sent, will get corrected back half the time. So it ends up that Eve actually corrupts 25% of the transmission that she actually manages to intercept, that Alice and Bob choose to keep. So she introduces 25% errors. And as I say, it doesn't matter. She can think of much more complicated eavesdropping strategies, but she's not going to get around this irreversibility of quantum measurement. There's a kind of trade-off between the amount of information that Eve can learn and the amount of disturbance that she will introduce. And that's built into nature, so she can't beat it. So after they've done a transmission, as I say, Alice and Bob can work out Eve's activity. Has she intercepted all of the key? If so, then I'm afraid they have nothing to work with. That's kind of called denial of service. So if Eve wants to just block everything and she manages to intercept everything, then she can deny service. So Alice and Bob have to try again. But if they've got some useful transmission, then they can eliminate the errors and distill down a key. And so these are examples actually from the very early experiments that were done to verify QKD. If Alice and Bob see a 4% error rate, then they can find the errors, remove them, and then they have to compress down by this kind of a factor. So by a factor of about 3. And in those final bits that they had a guarantee that Eve knows less than or equal to 1/1,000,000th of one of these bits. That's the most Eve can possibly know. So that these bits are pretty secure. If the error rate goes up, then you have to do rather more compression to get the same level of security on the bits that you keep. And this is not a linear relationship. So although I said it was 25% errors if Eve intercepts the lot, actually once these errors get into double digits, it's kind of not worth it. The amount of key that you can then start to distill is so small that it's not worth it. So if the errors are around 4 or 5%, you're happy. You can get really good distillation of key from that kind of a transmission. Well, where are we today? Well, working quantum key distribution systems exist, and they have done for quite a few years, and they use light. And that light may be sent via optical fibers. It may be sent through free space. Actually, both of those are options. And so, Alice can use underground fibers and send light signals to Bob at the quantum level, or she can send them through free space. And the very earliest experiments that were done used fiber under Lake Geneva and around British Telecom and in Los Alamos in the US. Over many tens of kilometers. Then people got it up to maybe 100 kilometers or so, and now with new protocols. So this is still with pretty standard fiber, but newer protocols, people have got up to many hundreds of kilometers. And actually, if you're prepared to do multiple hops, where you trust the nodes, as they're called, in between, they're trusted nodes, and one Alice passes stuff to one Bob on the next link, then in fact you can now get to thousands of kilometers. And the Chinese now have a network that's a couple of thousand kilometers long, with many trusted nodes in between. So fiber communications works over long distances, and so does free space. So in fact, the very first free space experiment, I think, was done in Malvern between a pub and John Rarity's office, but then they moved up to doing experiments over somewhat longer distances. So they did it between two peaks in the Alps over 20 odd kilometers, and then between two Canary Islands, 120 kilometers apart. And that distance has gradually moved up. And the reason for investigating that was actually not so much to do surface communications through free space, although those are potentially useful, but it was actually to work out whether you could get through sufficient atmosphere with quantum signals for satellite to ground experiments. And indeed, those are now working. And the Chinese have demonstrated that already with the Messier satellite that they put up a few years ago. And as I said, my silly cartoon at the beginning with Alice and Bob on the other side of the world, well, the Chinese have now actually sent entangled photons down to two telescopes that are 1,000 kilometers apart on the surface of the Earth. So distances are going up all of the time with quantum communications. That's the message, and it's out there and working. So that's where we are with state of the art. What I'm now going to do for about the last 10 minutes or so is tell you, first of all, a little bit about the UK national program in quantum technologies as a whole, but then about what we're doing in particular in the UK right now with quantum communications. And so this is what happened for the quantum communication, or sorry, the whole quantum technology community in the UK in 2013. So Christmas came a little early for us. It was George Osborne at the time was the Chancellor for the coalition government, and he found 270 million quid knocking around in his back pocket, which was really good, because that enabled the community in the UK to start up a new national program. And so that 270 million pounds kick-started a new national program to investigate the whole spectrum of quantum technologies, not just communications. And it took about a year to ramp up and put in place. And that program began in late 2014. And the first 5-year phase of it finished late last year. And we're now actually 1 year into a second phase too. And so I'll tell you a bit about what we've done in the last 5 years and what we're doing in phase two in the comm space anyway. And so this 270 million quid kick-started quite a number of different national activities, and I'm just going to focus on the ones concerned with the technology development in this talk. But there was a whole range of things set up. There were 4 big quantum technology hubs set up to deliver technologies. There's new centres for doctoral training. There was funding through Innovate UK for industry, and investment in the UK's National Measurement Lab, the National Physical Laboratory, and various other skills training stuff going on as well. So that was the initial investment, and phase 2 received a similar investment as well. But when you add in all the other money that's been invested either through industry or other investment from other stakeholders, then over the 10-year period, 2014 to 2024, the total investment is going to be about £1 billion. So it's a very substantial program that was set up in the UK. So I'm going to focus on the technology hubs, and in a minute just on one in particular. But what was set up were 4 technology hubs to kind of cover that technology space that I outlined at the beginning. And I've given these hubs their current names because all 4 of them have evolved into a phase 2, and so we'll be running till 2024 now. And so the one that's focused on sensing and timing, so this is using atoms to sense gravity very sensitively, to find buried infrastructure or holes in the ground that may turn into sinkholes and so on. You can use You can use atom interferometers to do that. That hub is led by the University of Birmingham. They're also collaborating with the National Physical Laboratory on quantum timing. And so that, if you like, is focused on atoms. So that's the sensing hub. In terms of imaging, which essentially uses light, but there are one or two other things that can be used for sensing and detecting certain things. But Glasgow leads the hub that essentially focuses on imaging with interesting states of light. So going beyond conventional imaging technologies with quantum forms of light. The quantum computing effort in the UK is led by the University of Oxford with all of their collaborators. It's currently called the Quantum Computing and Simulation Hub. Their focus in phase one was mainly on ion traps and photonics. They now include other platforms such as superconducting quantum bits and so on. So they broaden their portfolio in phase two. And part of the reason for doing that is that in addition to the computing hub, there is now a new National Quantum Computing Center. So this has been recently set up. It's the building is going to be built over the next couple of years, and if you like, the new National Quantum Computing Centre that will sit on the Harwell site a bit south of Oxford is a kind of tech transfer route for this computing hub. So they've now been able to broaden their portfolio, and they'll be able to transfer stuff to the new National Quantum Computing Centre. So that's the other three hubs. The one I'm going to tell you about for a few minutes now is the Quantum Communications Hub. So this is led from the University of York by me. I'm the director. And we focus mainly on quantum key distribution applications, but on quantum communications in general. And so I'll now tell you a little bit about what we do. The first thing I want to do is show you this slide, which tells you that this is not just a little project based at the University of York. This is a major national collaborative project that includes of the order of 10 or so universities, but it also includes very many industry partners, as you can see here, and national laboratories such as the National Physical Laboratory and institutions like the National Cybersecurity Centre support us with input as well. So it's a big collaborative project. Each of the four hubs will show you a similar slide. We're all spread out in superposition all over the UK. Each of us, we have partners that were pulled together to bring the excellence that we needed in the various R&D strands that we need, and we pulled in the industry partners that we need to collaborate with. So the hub is a big collaborative effort. It was quite when we were asked to bid for these hubs, right, big proposals and put them in, we were told very distinctly we should not be writing research proposals. We should be writing what I would call technology development proposals. And so we were supposed to take the outputs of the basic quantum research that have been funded over very many years in the UK, and we were supposed to turn those research outputs and push them towards working technology. So this is actually a cut and paste from what we said we would do in our proposal. We didn't say we'd do research, we said we'd develop new technologies. As I said, most of what we do is based on developing quantum key distribution further. I'll tell you a little bit about that in just a minute. We did some exploration of other forms of quantum communication as well. Our budget was 24 million plus a bit of extra we got for extending the network that I'll mention in just a minute. But we basically got a good fraction of that initial 270 million pound investment, and our budget for our second 5-year phase is very similar to this 24 million. So we will have had about 50 million pounds over the 10-year period, which sounds a lot of money, but when you share it out over all the academic partners, we are also, if you like, building all of our quantum technology R&D in this project on the basis of having been funded for many other projects as well in the past at the basic science level. So, as I've said, most of what we do is based on quantum key distribution. I've tried to hand wave and explain how that works in a simple way for you. And I just want to stress a few points about QKD before I move on and tell you briefly what we've been doing and what we're going to be doing. It's kind of obvious, I think, but the quantum aspect of the quantum key distribution is when Alice is sending quantum stuff to Bob and he's measuring it. After that, they do a bit of communication, work out their key. Once they've got their shared key, they can use that for various things. They could use it for secure communication, but they could use it as a rolling pin number, possibly for getting through a door or for a password or whatever. There's quite a number of applications. These applications are nothing to do with quantum physics. So this is using ordinary key material now, conventional data in a non-quantum way. So the quantum part is the distribution. The use is not quantum. Almost certainly whatever Alice and Bob are using keys for, the keys are consumables. So the protocol will say, use it once, then delete it. Don't use it again. So the keys are consumable. You have to delete it after you've used it, which means you have to top up every so often. And the top up is quantum in the same way that the original distribution is quantum. And as I've said, Alice and Bob have to have some way of checking that Alice really is Alice and Bob really is Bob. So they need some way to authenticate, which might be with some initial shared secret or some underpinning mathematical crypto or somehow. But Alice and Bob have to authenticate. And so those are the important points, excuse me, about QKD. But it's very important to note that the quantum part is the distribution. The use is not quantum. So what have we done over the first 5 years? And so here's a very quick overview in one slide. As I said, most of what we did focused on quantum key distribution. We kind of pushed it in 3 directions towards working technology. So the first one was to make it handheld. So this is for the consumers of the future. The idea is that Alice will be in your phone and Bob will be in the wall, and Bob will be owned by your bank or your employer or the government or whoever. So you as an individual can exchange key between yourself, your personal device, and those various institutions. And you know, that is now getting close. I think you can now even buy the latest Samsung Galaxy with the option of having a quantum random number generator in. So quantum technology is now beginning to get into phones, and you know, in a few generations' time, the aim will be that you'll have an Alice transmitter in a phone that you'll be able to exchange key with a Bob in the wall. So that was one direction we pushed QKD. Something else is doing both Alice and Bob on chip, and then you can put Alice and Bob chips in every computer in the future, and you can network things together in a quantum way if you wish. And so we pushed that forward, and hub partner Bristol did a lot of that work. They did the world's first chip-to-chip QKD demonstration a few years ago now. So that was a notable success from the last 5 years. We've also built a quantum network based on optical fibers in the UK. So we've got a network that goes, a little network that goes around Bristol, and one that also goes around Cambridge. We've got a connection that goes from Cambridge to British Telecom's HQ for their research and development, which is at Adastral Park near Ipswich. And we're borrowing bits of the National Dark Fiber facility to actually connect the network in Bristol and the network in Cambridge together using various trusted nodes en route. So we've built the UK quantum network in fiber. So it's not as large as the Chinese one, but the Chinese clearly need a bigger one because it's a very long distance between Shanghai and Beijing, and not quite so far between at the minute Bristol and Cambridge or any other 2 cities in the UK. So we built the UK's quantum network. We've done a bit of investigation of things that go beyond just key distribution, and I'll mention those again in just a minute briefly. But I do want to emphasize that we wouldn't have done any of this without strong industry collaboration. So this wasn't just an academic project with a few universities working together. It was involved very strong industry collaboration, and we built on that. And I think it evidences the fact that we've done very well with the collaboration, because we have seeded through the work that was done in the hub now quite a few projects that are now industry led. So they're funded by Innovate UK. ISCF stands for Industrial Strategy Challenge Fund. There's now a significant effort in the phase 2 UK national programme to fund projects through Innovate UK that are led by industry. And they're even further towards commercialisation and higher up the technology readiness level scale. So there's a tech transfer route now for outputs from all 4 of the hubs into Innovate UK projects. We worked on standards. Standards are very important for new technologies, that if you want stuff to work together and you want an international agreement about which protocols and how technology should work, then standards are very important, and we've worked on those, and we will be continuing that. We also used funding from the last 5 years to seed 1 or 2 projects that are fed through into what we're doing in the next 5 years. And so this is the vision for the phase 2 hub. So we're about a year in now. We started late 2019, and as I say, we had a similar budget to phase 1, and we're pursuing quite a number of things. We expanded the portfolio a bit. We're certainly going to continue expanding the UK quantum network, the fiber-based network, and we'll be adding bits and pieces to that and using it for various demonstrations and examples. We're looking at new ways to do QKD, so based on continuous light signals, or although I said I wasn't really going to talk about it today, based on distributing entanglement, because if you can distribute entanglement, you can certainly use it for key distribution and actually other protocols as well. So we're looking at different ways to do QKD. We're continuing the handheld work to make it genuinely handheld, so it really can be Alice in your phone in the future. Perhaps the biggest thing that we've introduced in phase 2 actually is quantum key distribution in space, to learn a bit more about the capabilities and what's going to be required for setting this up as a future, if you like, commercial service. We want to do some investigations using a small CubeSat. So this is a satellite that's literally, let's say 30 centimeters by whatever. It's that kind of size. You can put a quantum transmitter up there, and then you can have a ground-based receiver, and you can send quantum signals from Alice in the satellite to Bob on the ground, and share key between those two. So we've got the plans to do that. So that's the major addition to, I think, our phase 2 portfolio. We're continuing chip-based work. Some of that, as I said, is already tech transferred out into Innovate UK projects, but we're continuing with some more fundamental investigations into new aspects of chip technologies. We're pursuing new protocols, things that go beyond key distribution, which might be random numbers, but they might also be various other forms of things that are not just key distribution, but will be useful in security scenarios. We're developing detectors and sources that we need for the Alice transmitter and the Bob receiver. We'll continue our standards work, because standards are always going to be important, I think, for technology development. And we're also looking to combine quantum stuff with new mathematical cryptography. And I've got one final slide on that in just a minute. And so clearly it's important to test what we do to make sure that things do what they say, and the National Physical Laboratory is a key partner in doing that kind of testing. Okay, so final slide on the impact of quantum technologies as a whole for security, because this is a very important issue. I mentioned very early on that the quantum computers have the potential to do cryptanalysis that we can't do with ordinary computers, and there is a looming threat. So the threat is that a sizable quantum computer, much bigger than the ones that currently exist, but a sizable quantum computer will be able to break the current asymmetric public key cryptography that we use to underpin probably most of the internet sessions. As a secure internet session boots up, you use PKI to exchange keys to set that session up, and so that will become vulnerable, because the mathematics that underpins the asymmetric crypto is going to be vulnerable to a quantum computer. And you may think, well, you only have to worry about that when the quantum computer appears, but actually you don't. If you're worried about the data that is currently being sent around and potentially being recorded as encrypted data, if you're worried about the security shelf life of that needing to be quite long, and it takes quite a long time to retool all of the secure hardware that we've got that supports the current internet, then actually if the sum of those two numbers is bigger than the time to a big quantum computer appearing in the future, you should be worried now, not when the computer appears. And so that is a looming problem. And some people are already concerned about it because this equation may tell them that they should be worried right now. You might also be worried that new quantum sensors will actually enable us to have cheeky looks at things and image them beyond current limits. But the good thing is that we know already that despite all of this stuff, the kinds of secure quantum communications technologies that I spoke about, such as quantum key distribution, cannot be attacked by any of these other new quantum technologies. So that's very nice to know. At least we've got a plan going forward. In addition to that, because of the vulnerability of the current mathematical crypto that's used to underpin many of our secure communications, there's a big effort to develop new mathematical encryption. So this is encryption that at least cannot be cracked with the current algorithms that we know that we could run when we have a big quantum computer. And so people are working on both of these. Obviously, I'm working mainly on secure quantum communications, but there's a large effort on new mathematical crypto. And this mathematical crypto is actually being assessed at the minute in a kind of worldwide process, but the assessment is led by the National Institutes for Standards and Technology in the United States. And so they're overseeing this process worldwide to come up with the new mathematical crypto. And I think the safest way to think about moving forward is actually to use both of these things. The mathematical crypto that is thought to be immune to all of these quantum algorithms that we have that could run a large quantum computer, and things like quantum key distribution as well. So I think that the best way forward that we have to look at the minute for secure communications in the future is going to be a combination of these two technologies. Okay, so my final slide is simply a set of links that people might be interested in following up on. So I'm just going to leave you with those, and you can note them down at your leisure. But anyway, thank you very much for listening, and I'm very happy to take any questions.
Right, Tim, that was absolutely fantastic. I think we're nothing except for the generosity of people like yourself coming over and doing these talks, and I think it's probably something we haven't done for such a long time. And I know there have been some great questions. So if we perhaps take a few of those, spend a few minutes answering those. So
Sure.
Chris Anderson's asked a couple of questions, one of which is very upsetting, and that is, do you think that all this work that's being done might be affected by Brexit? I'll leave you to answer that question.
That's a very good question. I think there certainly will be some effect. I mean, I think the issue we have is that we don't know what's going to happen with our collaborations with our European partners going forward. At the minute, it's not entirely clear. The collaborations that we're currently in and involved in, and we have been a very strong collaborator into Europe, those are still ongoing, and we were given a guarantee that those will run their course. But I think until it's decided exactly what sort of partner we are in the future EU, it's not clear exactly how we're going to collaborate. But it's not all doom and gloom, because, for example, Switzerland is not in the EU, and they have a deal where they participate in EU projects. They pay their way, as it were, and so there is certainly scope for future scientific collaboration with the EU. I think it's more debatable when it comes to things like the GPS system that is being developed in the EU, whether we will remain partners in things like that. So I think we have to think carefully about some aspects of what's happening in the EU. But from the research perspective, at least at the basic level, and the lower technology readiness level, so the early stage development, I think there's still scope for European collaboration there. So I think we're intending to continue that. But I think there is a danger that at the higher technology levels, there could be an issue with future work with Europe.
Yeah, okay. And Chris also asked a question about whether Manchester University was involved in the NNQTH Quantum Technology Hub. What's NN stand for? Is that National Network Quantum Technology Hub?
They're not a partner in our hub, but there are people in Manchester who do certainly some quantum work, and so I think there are collaborations, but I don't think they're certainly not a partner in our hub.
Okay, I've also got a question from Hamza Munam, who asked, where is quantum technologies used in the aerospace, engineering and astrophysics field?
In terms of astrophysics, I think not just astrophysics, but fundamental science as a whole, there is now a look back, if you like, towards fundamental science in general, and there was a whole call for proposals, and some of those are now funded and starting up, for using quantum technologies as tools in fundamental science. So not just in astrophysics, but all sorts of fundamental physics and fundamental science in other areas. So you will see, I think, over the coming years, an emergence of the application of quantum technologies back as tools to further investigate fundamental science. So that's certainly true. In addition to that, one of the applications of quantum computing is to simulate other quantum things. So I think people think quantum computers will be widely applicable for investigating complex molecules and simulating pieces of new material and things like that. So I think there is scope for certain quantum technologies to certainly feed back into fundamental science. In terms of aerospace or finance or other industries, there's certainly application for secure communications, if those are relevant in those situations, but there's also application of quantum computing for perhaps optimizing problems and things like that. And so I think you will see take up of this. I mean, I think the fact that every single one of the 4 hubs will show you a slide which is completely full of industrial partners, and some of those are the big ones that you might expect. So for us, for example, we have BT, who are one of the main comm service providers in the UK. So I think you'll find that every single hub has a few of these large partners, as well as many smaller companies and startups and so on. So the applications are now beginning to emerge, and that's why industry is now getting much more involved in this area. So I think over the coming years you will see applications of these things emerge. I mean, with quantum computing at the minute, we're only at the level where there's just about a quantum advantage emerging. So in a few years' time, you may actually see really useful problems being attacked with those.
Okay, thanks, Tim. That was very useful. Faisal Ali's asked a question similar to one I was going to ask. Really, the question is, can physicists do quantum, or are they the only ones to do quantum technology? And I was going to ask about if there's lots of college students here and perhaps school students might be interested in getting involved in quantum technologies. How do you do that? What is that journey? We know about yours, but are there other routes? I know you're at York. If people were interested, if this really switched them on,
yeah,
well,
I can start to illustrate that by if I put my other hat on now, instead of director of the Quantum Communications Hub, I say I'm director of the York Centre for Quantum Technologies. Well, that centre involves academics working together from physics, from mathematics, from electronic engineering, from computer science, and in some places chemists also get involved. And so the scope for people to get involved in quantum technologies goes right across the sciences, and people are now thinking about whether there are quantum effects going on in biology. So perhaps in one particular direction, it even extends out to that. So I would say that there's potential to get involved from essentially any of the sciences, but particularly as things develop more towards technology, engineering is becoming more and more important. So I'm a physicist, but in the end, this stuff is going to get built and designed in the future by engineers, I think, whereas the algorithms will be worked out by mathematicians and computer scientists, and the physics will be providing, if you like, underpinning quantum support. So I think there is scope for everyone to get involved, and I think it doesn't matter at the undergraduate level what degree you do. If you do something in the sciences that's relevant, then the scope for certainly a lot of it at the minute, people are also then pursuing doctorates because they want to get quite specialist. But I think in the end, when the technologies start to emerge, it'll be like ordinary IT. People will use it without necessarily knowing about the guts of how it works. So there'll be all sorts of applications where people can use quantum technologies for whatever without actually so I don't think you have to have a degree in quantum physics if you want the flippant answer. I think there is plenty of scope for people utilizing quantum technologies without actually understanding the details of the quantum physics that underpins it.
Okay, thank you. And I'll take one more, which sort of we've got gone on over 10 minutes, but this is from Michael Murphy. And Michael asked, what were the biggest challenges in implementing terrestrial QKD over, and I haven't got the last part of the sentence, over something, oh yeah, over the last 20 years?
Well, I think there are two basic directions. There's doing stuff in fiber, and then there's doing stuff in free space. I think they present different challenges. So the challenge we set ourselves with fiber is that we want to utilize ordinary fiber that's already in the ground. So it's not special low loss fiber that's put there just for quantum comps. We want to be able to do QKD over ordinary fiber. Now, the one thing you can't do with QKD signals is shove them through conventional optical amplifiers because they will scramble up the signals. So we have to work around where there are optical amplifiers, which is why you can't use undersea cables that run through those. But in general, the challenge was set to use conventional fiber that's already in the ground, bog standard comms fiber, and I think we've demonstrated that can be done. And so that was the biggest challenge there. I think the challenges still exist with the longest distance free space communications because the Chinese and one or two other experiments have demonstrated the feasibility of that. But at the minute, you wouldn't say the data rates are useful for communications. What they've done is they've done beautiful scientific experiments that show that these things can actually work at all. And now we've got to work out how to do that better and get the data rates up. So I think there are still challenges there, but it sounds pretty amazing when you think about it that you can even send quantum light signals from a satellite and catch them on the ground.
Yeah.
So I think the fact that that's been proved to be possible was a really big step forward, and now we have to build on that and get the data rates up.
Okay, Tim, I'm going to stop there. I think if there's one or two questions that haven't been answered, I can't really see them here. We can perhaps send them to you, and we can individually answer them if you didn't mind.
I'll be happy if you send them to me by email. I'll be able to pick out answers and send them back, and then you can pass them on. That'd be fine.
Right, but I'd just like to thank you once again on behalf of the Institute of Physics. We'd love you to come back and do another talk. And I hope everybody has a great Merry Christmas and a nice safe Christmas. Wash your hands, wear a mask, and we'll be back in the new year with another talk, and we'll post that out on the IOP website as to what that will be. We're thinking it might be something in the Apollo moon landings, but it's still uncertain, a bit like quantum technology. So, Tim, thank you very much. Thank you, everybody. We'll end the meeting there, and we'll see you all again very soon indeed. Thank you.
Great. That's super. Thanks very much. Bye.
Bye.